Okay, so I thought we could maybe walk through this problem together. This is a kinetic friction problem that involves an imbalance of forces, and you know, it's a spaceship, right? So a spaceship loses power, it crash lands on Earth, and it kind of slides across this snowy field. Okay, and we know how fast the spaceship is moving as soon as it hits the ground. Right, it hits the ground, it starts sliding across the snow at a velocity of 20 meters per second, and has this kinetic coefficient of friction equal to 0.24. And without knowing the spaceship's mass, we want to know how many meters does the spaceship slide across this snowy field before it stops. And it's a problem that just sort of forces you to use the kinetic frictional force, right, that opposes the direction of movement, right, to determine how much that force will decrease the acceleration, right, all the way up to the point where it just stops. Okay, so as usual, right, the first thing you probably want to do is just sort of take stock of what you know and what you don't know, and draw a free body diagram, okay, to just sums up all your force vectors. So we can just do that right here on this picture. Here's our spaceship, okay, and we can just think about what forces are actually acting on this object. Okay, so it has a weight, right? We don't know what its mass is, but it has one, whatever it is. And what we know is that, right, this force vector is going to point down. Okay, this would be its weight, right? Okay. And then, as per Newton's third law, we know, right, that in response to this force being applied perpendicularly to the surface that is the snowy field, right, we're going to have another force vector that points in the opposite direction and that responds, essentially, right, and matches that downward force. And it's going to become important further on in the problem, and we would call this the normal force, right? Fn. Okay. So that really takes care of the forces in the y-axis. Remember, this is not moving in the y-axis. It's only moving in the x-axis. Okay, it doesn't mean it doesn't have force vectors, right, in the y-axis, but they're balanced, right, is what we're going to see as we go forward. So in the x-axis, then, what forces are then acting on this ship? Okay, well, we know that there's friction between the ship and the snowy field, and we're given a kinetic coefficient of friction, right, that describes the frictional relationship between an object and a surface that it's trying to slide past while it's already moving. Or you may have experienced this in your life, where you try to push a box across a floor, and it becomes easier and easier to push as the box starts to move, right? That's the difference between static and kinetic friction. This thing is already moving. So we're given a kinetic coefficient of friction. And the higher it is, the more frictional force is produced by its relationship with the surface, okay? And we don't know what that total magnitude is yet, but we know that there is one. And we know, let's just assume that this ship is moving to the right here. So let's call this the x positive, okay? Let's call this the x negative, okay? This is the y positive, the y negative axis, okay? We know that there is a force vector, right, opposing the direction of movement, right? And so we'll call that our kinetic frictional force, or our Fk, okay? Now, it's important to note that even though this thing is moving, it's moving, right, in the positive x direction. It doesn't have a force in that direction, right? It's just purely just the momentum of its movement previous to hitting the ground that's carrying it forward. Okay, so it doesn't have like a thrust. There's nothing driving it forward other than that momentum. And so in the positive x direction, there really is no force. There's no force vector. And so these are basically all the force vectors that are going to act on the ship. Okay, so I think by looking at this, we can agree that there is an imbalance of forces here, right? Not in the y direction, but definitely in the x. We have force dragging back towards the negative x direction and nothing driving it forward in the positive x direction. And what does Newton's second law tell us about an imbalance of forces, right? If the sum, right, of all forces acting on an object, right, equals mass times acceleration, okay, as per Newton's second law. Now what that tells us is, as long as this sum of forces isn't zero, right, acceleration will not be zero. Right? The only way you can get a zero acceleration here is if the sum of all forces also equals zero. And so what the second law actually says is that an acceleration will be produced by a net force, right, in the direction of that force. Okay, so if we have this imbalance of forces, we're going to get an acceleration, but look at where the net forces actually are, right? They're in the negative x-axis. And so this acceleration is going to likewise be negative, or what you would think of as a deceleration, right? Our velocity is going to be changing, right? But it's going to be changing in a way that makes it smaller or that reverses it in the opposite direction, right? However you want to look at it, up to the point where the velocity just becomes zero. Okay. So let me just erase this here. Okay. So we can relate this back to the kinematic equations. Okay, so just to show you what I did here, just in case that's not clear, right? It's sort of a cleaner version of this free body diagram, right? We have our spaceship, positive x, positive y, negative y. We have our weight, we have our normal force, basically matching the weight, since the weight is the only downward force, or the only force pressing down on that surface, right? And then we have the kinetic frictional force, right, dragging it back into the negative x direction, and really nothing in the positive x direction as far as force goes. Okay, so let me go back here. All right, so we're not given a time variable, right? We don't know how much time it takes for this to go from hitting the ground to stopping. But we're asked to find distance. We're asked to find basically delta x. So if you look at your kinematic equations, right, you'll see an equation that relates the change in velocity to acceleration and change in distance. Okay, and one of those variables in the change of velocity we absolutely know. Actually, both of them we know. We know the initial velocity, it's 20 meters per second. We know the final velocity. Final velocity is just going to be zero. That's what stopping is. Your velocity just reaches zero. So that equation is this. Okay, so the final, let me switch back to my marker. Okay, the final velocity squared, right, is going to be equal to the initial velocity squared plus 2 times the acceleration times delta x being the displacement that this object experiences. Okay, so this is the equation that we're going to use to determine our delta x. And all we need to do at the moment right now is just solve this for delta x, and then we can start to worry about filling in the variables. So what I would want to do here, and there's a couple of different ways you can do this, but what I'm going to do is I'm going to subtract the initial velocity squared from both sides. Okay. And then once I do that, I'm going to end up with v squared minus v naught squared equals 2a delta x, right? And at that point, if I want to solve for delta x, all I would really need to do is just divide both sides by 2a. Right? This cancels, that cancels, okay? Now let me rewrite this. I don't really have a lot of room on this little picture here, right? But just erase it and I'll rewrite it in its proper form. delta x going to equal v squared minus v naught squared divided by 2a. Okay? So I hope that makes sense, right? And because we know that the final velocity is 0, right, we can already see that this is going to be a negative change in velocity, right? Whatever, so the initial velocity is 20, right? The final velocity is 0, right? Our change in velocity is going to be negative 20 meters per second, right? Over whatever amount of time it takes for that to happen. So we can fill in these variables very easily, but it's A that's kind of the problem. So you may have noticed, right, I think I mentioned at the beginning of the problem, that I left mass out of the problem. We don't know what this spaceship is in terms of mass, right? And because of that, we really can't know what the weight is. And because we can't know what the weight is, it becomes really difficult to know what the normal force is. And if we don't know what the normal force is, if you remember your definition of the static or the kinetic frictional force, right? It can be really hard to know that as well, because the frictional force essentially equals the coefficient of friction multiplied by whatever the normal force is, whatever force is matching, right? The downward force that's being applied to an object trying to move across a particular surface. So we have to do a little bit of algebra here to get around this problem. It's not a dead end, it's just an obstacle. So we don't really know what A is at the moment, but this is sort of a valuable skill, right? Where if you don't necessarily know what to fill in, right? If you don't really know the value directly for a given term that you need in an equation, you can start to think about alternate definitions for that term and fill those in, right? Because you may eventually find an alternate definition that that is satisfied by the information that you have, right? Or you may find a way to cancel out a variable that you don't have, right? Thereby making it irrelevant. So we'll see what we can do here. Let's try to define A. We know from Newton's second law, I just said, right, the sum of all forces, right, will equal the mass multiplied by the acceleration of the object that those forces are acting upon, right? So if that's the case, if the sum of all forces equals ma, right, then A would simply equal the sum of all forces divided by m, right? And I'll qualify this by putting it just in the x-axis. We're only working in the x-axis here. So acceleration in the x-axis will equal the sum of all forces in the x-axis divided by the mass, okay? And again, we don't have the mass, right? But we do know something about the sum of all forces in the x-axis. We know that the kinetic frictional force is really it. That's it. That's the only thing acting on this spaceship in the x-axis. So we could just substitute this into the sum of all the forces in the x. So what we could say then is actually, we could say A is equal to the negative, right, kinetic frictional force over m. Yeah, erase this guy here. Okay, so you might be saying to yourself, okay, great, who cares though? We don't actually know what the kinetic frictional force is. Well, this is when we start to substitute again. Okay, we don't know this term, but maybe we can think of an alternate definition for this one once again that might be satisfied by something that we have. So what is the mathematical definition of this? Well, I happen to know that the kinetic frictional force, is equal to the coefficient. I'm going to draw a weird U thing here. This is a Greek mu. Okay. It looks like a 4-year-old drew it because I'm using my PowerPoint as a whiteboard. But this is equal to mu k, or the coefficient of kinetic friction, multiplied by the normal force. Okay? So once again, I will substitute this in for our definition of A. So what I know is that A will then be also equal to negative coefficient of kinetic friction times normal force. Okay. And then let me get rid of this once again. And now you may also be asking yourself, right? Again, who cares? We don't know what the normal force is. We know what the coefficient of kinetic friction is, right? It's given to us in the problem. It's 0.24. We don't know what the normal force is. Okay. So now we just need to use a little bit of intuition, right, to think about what the normal force is equal to. And we've kind of alluded to this multiple times as we've written out this problem. So because the only downward force acting on this spaceship is its weight, there's really nothing pushing down on it, right? The normal force in response, in accordance with Newton's third law, should match W, right? It should be basically the same in magnitude, right? If different in sign, right? To the weight, okay? So if the weight of the spaceship then equals its mass times G, right, which is 9.8, okay, then the normal force in magnitude, right, should also be equal to the mass of the spaceship times G. So what might be going on in your brain right now, and you also might see exactly what we're doing, right? But you may also be asking yourself, again, why do I care? We don't have the mass of the spaceship. Why are we just making more m's for ourselves? Well, let me show you. So if I know that this is the definition of the kinetic frictional force, right, and therefore the sum of all forces in X that I need, okay, now what I can do is just erase the thing I don't know, and then put in, once again, a substitute definition for that thing. So I know that the normal force will be equal to mass times gravity. Okay. And look what happens to M. Bam, bam. It just cancels out. So we don't actually have to spend 1 second of our lives worrying about what the mass of the spaceship is, right? It just cancels out and we don't have to worry about it. And we end up with a definition for A, where A simply equals negative mu k times G. There we have it. There's our A. Let me erase all this other nonsense here. Okay. There's our A. Okay. Now we can just substitute that in. We just substitute that into our original equation and solve for delta x. Okay, because we know everything else. So let me rewrite this equation. Okay. Actually, I'll leave that there. Let me just erase A here. Okay. And so it's going to be 2 times negative k multiplied by G. And you see that this term in the denominator then becomes negative, but no worries, because this term in the numerator was always going to be negative in the first place. Negative divided by a negative is a positive, and we stay true to our displacement in the positive x direction. So with that said, let me punch in some values here. Okay. So v squared is 0, correct? Okay. V naught squared, so we're going to get 20 meters per second. That's our initial velocity, 20 squared, divided by 2 times let's put some parentheses around here, right? Negative 0.24 okay, times 9.8. Now, if you were to do this, right, you get negative, right, 20 squared, right, divided by negative 0.24 times 9.8, right, times 2. What you should get here is roughly $85 meters. If you round down just a little bit, okay? So, spaceship loses power, crashes on Earth, right? Hits that field at 20 meters per second, right? Given the frictional relationship, the kinetic frictional relationship between the ship and the snowy field, it will skid 85 meters before it is done, okay? So I hope that made sense, and thanks for watching. Okay.